All right, so okay, so we got this limit problem. We got the limit. We got the limit as x goes to 0 from the right of 9x times the tangent of 5x plus pi over 2. So the first thing I want to think is, okay, well, what do I get when I do direct substitution? You know, kind of that's the first thing you should always check is, you know, what happens if I just plug in 0? So, okay, well, so obviously if I plug 0 into this first part, that first part is going to go to 0. So 9 times 0 is 0. And now, okay, this one's a little bit trickier here because as x gets close to 0, well, this 5x is going to get close to 0. And that means that we're just going to wind up with a pi over 2 here. And the problem is that the tangent has an asymptote at pi over 2. So here, this is a graph of the tangent function, and the tangent function has an asymptote at pi over 2. And so the issue here is that I kind of have to know, the idea here is here's what I'm getting at. This guy is this is going to go to either plus or minus infinity. And I just have to figure out which one. Although I guess technically it doesn't really matter which one, but it matters to me because I want to say the right thing. So, because again, wait, let me be clear. Why is this going to go to plus or minus? I want to make sure we all understand why this is going to plus or minus infinity. Because the idea here is this 5x, when x gets close to 0, this 5x is going to be 0. Or it's going to be close to 0. This 5x is going to be close to 0. And so that means that this inside here is going to be close to pi over 2 because we got a pi over 2 plus something that's close to 0. So, and then if I look at the graph of the tangent function, well, when x is close to pi over 2, then the function's either really big or it's really, really negative. And so that's how we're getting plus or minus infinity here. But I think we can say even more. I can narrow it down because since x is we're taking the limit as x goes to 0 from the right. So that means that this 5x is a positive number. This 5x is close to 0, but it's positive, which means that what we've got here is pi over 2 plus a little bit more. And so that's putting me on, that's putting me on this side. If I'm, you know, if I'm adding a little bit to pi over 2. And so that's going to put me on the right side of pi over 2, which is meaning I'm going to be going towards negative infinity. So that is actually going to negative infinity. Okay, so the point is we have this this limit is 0 times infinity to 0 times negative infinity, and you might be tempted to say that, oh well, that's 0, right? Because 0 times anything is 0, and yeah, that's tempting. But it's wrong in this case. Well, no, it's not wrong to say 0 times anything. 0 times any number is 0. That is 100% correct. But the problem is infinity is not a number. So saying 0 times infinity technically doesn't make sense. You can't do arithmetic with infinity. So basically, anytime someone says 0 times infinity, you should say, wait, that's not really legal. That what you're doing is breaking the rules of mathematics. And another way to think about this, and really the right way to think about this, the correct way to think about this, is this number is not actually equal to 0. It's just close to 0, because x is never equal to 0. X is just close to 0. And so this number isn't actually 0. The arrow just means it's close to 0. And this number, likewise, this number is not negative infinity. It's just a number that's close to negative infinity, whatever that means. I mean, maybe another way to say it is it's a really big negative number. And so then you can see the error in trying to multiply these. You can see why there's a big question mark here. Because what if I said, here's a question for you. What do you get when you multiply a number that's close to 0 by a really big negative number? And the correct answer to that is you should say, well, it depends. I mean, it depends upon how big this number is. And it also depends upon how close this number is to 0. So that's really what's going on here and why this is an indeterminate form. So anyway, so I'm sorry if I went on, if I rambled on there for a while, but L'Hopital's rule and these indeterminate forms, they're kind of weird and mysterious the first time you see them, but they really do make sense if you think about them. And so I want them to make sense for you. And so I'm trying to explain them in many different ways in the hopes that one of those ways will resonate with you and it'll make sense. Okay, but anyway, so the point is let's get on with the story here. The point is this is an indeterminate form. This is a 0 times infinity indeterminate form. And so if someone says, what's 0 times infinity? The correct answer is, I don't know, it depends. So we have to, that's what we have to use calculus for. And okay, so now, so you say, okay, well, how are we going to use calculus? And yet that's a great question. How are we going to use calculus? So, okay, well, let me write the limit down here so I can get in the spirit of things. So I got the limit as x goes to 0 of 9x times the tangent of 5x plus pi over 2. Okay, so we know that this is a 0 times infinity indeterminate form. And so whenever we have an indeterminate form, I want you to think about L'Hopital's rule. So, all right, so I'm thinking about L'Hopital's rule. But I say, wait, Travis, I thought that you can only use L'Hopital's rule when you have a fraction. And that, if you're thinking that, you are 100% correct. That I cannot use L'Hopital's rule on this right now, because it's not a fraction. L'Hopital's rule only works if you have fractions. So I'm sort of stuck here. So the way to get around that is to be sneaky and to introduce a fraction where there maybe wasn't one before. So the idea is that I could rewrite this as, let me think here. So wait, let me do a little bit of arithmetic down here on the bottom, because what I'm about to do is a little bit tricky and I want to make sure we understand it. So tangent, so I'm going to do some algebraic sleight of hand here. So the idea is multiplication and division are kind of the same thing. And you might say, what? That sounds crazy. I thought they were opposite things. Well, yeah, I guess you could think about it that way. They're like they're two sides of the same coin. So they're on the same coin. And so the moral here is that, like, let me see, yeah. So I got tangent, and what if I make that 1 over tangent? Well, hey, well, 1 over tangent, that's the same as cotangent. Oh, well, okay, well, now how about I flip both sides then? So that means that tangent over 1 is equal to 1 over, because I can think about this as over 1, is equal to cotangent over 1. So the moral is, what just happened there? I said that, okay, yeah, 1 over, so hopefully you agree with me. What I did was sort of fancy, and it might have went past you fast. But 1 over tangent is equal to cotangent. That's a definition. And okay, well, now let's flip both sides. If you have 2 sides of an equation, you're allowed to flip one side as long as you flip the other side. And so we have tangent is equal to 1 over cotangent. And so that's actually really useful here, because now I can say this 9x, instead of writing a tangent here, I can write 1 over cotangent. So this will be cotangent of 5x plus pi over 2. So, and now I have a fraction. So that was kind of a dirty trick. But that is a dirty trick that should be in your bag. It should be in your bag of mathematical dirty tricks. So we should all have a personal toolbox of mathematical dirty tricks, and that should be one of them. Essentially the idea is this: multiplication is really the same as division. Because 3, what do you get when you do 3 times 2? Well, okay, you get 6. But what do you get if you do 3 divided by 1/2? So what did I just do? I changed this multiplication to a division, and I did the reciprocal of the 2. You also get 6. So the moral is that you can always turn a multiplication into a division as long as you do a reciprocal to one of the components. And that's essentially what we did here, is we took this multiplication and we turned it into a division, but we had to then do the reciprocal of tangent to make that work. Okay, so that was kind of fancy, and so you'll have to practice that on your homework when you do these. And okay, but the point is, I'm not done with this problem yet. I'm just getting started. So what happens now is, now it's safe, or now I think I might be able to use L'Hopital's rule, because what was it? I now at least have a fraction. That L'Hopital's rule says you have to have a fraction, and okay, well, at least I've got a fraction now. But you have to be careful, because just because you have a fraction doesn't mean you can use L'Hopital's rule. You have to check that you have an indeterminate form. Okay, well, so let's think about what happens here. Well, as x goes to 0, clearly the numerator is going to 0. No problem there. And then, okay, let's see. The denominator is a little bit more complicated. Well, as x goes to 0, that guy is going to 0. And that means that this whole thing then is approaching the cotangent of pi over 2. Because if this piece is going to 0, then all you're left with is the pi over 2. And the cotangent of pi over 2, you can check, is 0. So hey, okay, so this is good, because now we have a 0 over 0. So this is a job for L'Hopital's rule. We are cleared to use L'Hopital's rule. So all right, so let's use L'Hopital's rule then. So we're gonna have, so let's see, so we'll use L'Hopital rule here. So we got the limit as x goes to 0 from the right of, okay, so the derivative of the top is easy. The derivative of the top is just going to be 9. And now the derivative of the bottom, oh boy, this will be a good one. So there you go. So pause the video and ask yourself, you know, check your understanding. Can you find the derivative of cotangent of 5x plus pi over 2? And all right, so the video is paused now. And let me actually, why don't I ask? Okay, so yeah, so the derivative of cotangent is like cosecant squared of, and then there's the 5x plus pi over 2. Okay, but wait, there's a couple things that this is not, if you're thinking, I'm not sure if that's right, Travis, you're right, because there's a couple things missing. One is there should be a negative here. Because remember, the derivative of a co-function is always has a negative in front of it. And then the other thing that you want to make sure that you don't forget is the chain rule. That there's an inside function here, right? This is the inside function. And so whenever you find the derivative of something with an inside function, you then have to multiply by the derivative of the inside. And the derivative of the inside is just 5. So you need to multiply by this 5. Okay, so if you got that, then you passed Math 75A. And if you didn't get that, then you need to make some flashcards and review. Okay, so anyway, so we're not done yet, but we're getting in the home stretch here. So okay, well let's clean this up now. So let's cross our fingers and hope that this is something nice. So I've got the limit as x goes to 0 from the right. Okay, so let's see what we got here. The 9, I'm going to factor out the 9/5, the negative 9/5. You know, the 9, that's just a number, and numbers don't scare me. So I'm just going to get the numbers out in front. And so I can separate the easy stuff from the hard stuff. And so if I think about this for a minute, well, this is cosecant is the reciprocal of sine. So right, so let's think about this. 1 over cosecant squared of x, that's the same as 1 over 1 over the sine squared of x, right? Because cosecant is the reciprocal of sine. Oh, and now I have a double fraction. So that just means that's just equal to sine squared of x. So the moral, this was just scratch work down here. So ignore that. But that's just justification for the step I'm about to do here. So here we have a cosecant in the denominator. But what this little scratch work shows me is I can bring that cosecant out of the denominator but I have to turn it into a sine. So this turns into then the sine squared of 5x plus pi over 2. All right, and now this is a good thing, because now I think I can just plug in 0. So if I plug in 0, well, that piece is going to go to 0. And so what I'm left with is I'm just left with negative 9/5 times the sine squared of pi over 2. Because the x turned into a 0. And so this guy is going to 0, so the pi over 2 is the only thing that's left. And hopefully you remember that the sign of pi over 2 is 1. So this is negative 9/5. Woo! So there you go. So that's what I love about these problems. So what just happened here? So remember, let's think about what happened here. The problem started with 0 times infinity. So I can imagine that your 6-year-old cousin could come to you someday and say 0 times infinity, that's equal to 0. And you would be completely correct if you said, no, 0 times infinity is sometimes equal to negative 9/5. And we just proved it. What we sort of proved here is that sometimes 0 times infinity is negative 9/5. Who would have guessed? I certainly wouldn't have guessed that. But serious, and so I'm kind of joking there. So, I mean, I am being a little bit, I am joking a little bit here. So let's stop joking and be clear. The 100% correct thing to say is if your cousin says 0 times infinity is 0, you should say, well, technically that's not correct. Technically 0 times infinity is an indeterminate form. And what that means is that 0 times infinity doesn't have a set value. And what that means is that it means essentially what we saw here, that in some situations, 0 times infinity will be negative 9/5. In other situations, 0 times infinity could be 27. I could make up a problem where 0 times infinity was equal to negative 42. So the point is that's kind of what makes an indeterminate form indeterminate, is it could kind of be anything. And it just all depends upon what the function is. So anyway, kind of a cool thing, because at the beginning I saw that this was 0 times infinity, and I never would have guessed that it was 9/5 or negative 9/5. So to me that was fun. And now looking back at the problem, you can see that, oh, well, the 9 and the 5, the fact that there was a 9 there and a 5 there, that's not a coincidence. So you could probably modify this problem and get whatever number you want here. So that would be fun, actually. Yeah, you could think about your favorite number. If your favorite number is 17, then if you change this number to a 17 and you change this number to a 1, then your answer would be negative 17. So that's kind of fun. Okay, I should stop recording now.